do some more operations on series. In particular, you could multiply series. Let me show you what I mean. Here's an example. Let's find the series for e to the x times sine of 2x. So I know the series for e to the x. I know the series for sine 2x. I'll write those down. So the series for e to the x starts with 1 plus x squared over 2 factorial plus x cubed over 3 factorial. That goes on forever. And I know the series for sine 2x. It's 2x minus 2x cubed over 3 factorial plus 2x to the 5th over 5 factorial, and so on. You could pretend that these are just really big polynomials. You could just do a huge FOIL operation, collect terms, and that would be the series expansion for e to the x sine 2x. So you just multiply everything out. So for example, I do 1 times 2x. So I start with 2x. Then I would do x times 2x. That would give me 2x squared. Then I do 1 times this term. So that term there is 2 cubed over 3 factorial. I think that's 8/6 x cubed. And I could also get an x cubed by multiplying x squared over 2 factorial times this term. So if I multiply these two circled terms together, I think I get plus x to the 3rd. I can get x to the 4th powers. So how could I take something in this first parentheses, something in the second parentheses, multiply them, and get an x to the 4th? Well, I could do this boxed term, the x cubed times the x. That would give me an x to the 4th. Or I could do x times this x cubed term. That would give me an x to the 4th as well. So let me write that down. X to the 4th power. The box term times this will give me 2/6 x to the 4th. And then the x term times the x to the 3rd term would give me minus 8/6 x to the 4th. Then you can keep doing this forever, as long as you want. So you get the series 2x plus 2x squared plus 1 minus 8/6 x to the 3rd plus 2/6 minus 8/6 x to the 4th, and so on. So it's a big, long process. Computers could do it really quickly, so you'd never really do this by hand in an application, but I'd like you to know that it's possible. And I'd like you to practice once or twice by hand just to see what's going on in the exercises. But you can multiply two series together. You just do a huge FOIL term. Let's do one more example of multiplication. What if I had the series 1 over 1 minus x times 1 minus 2x? Well, I could write this as 1 over 1 minus x times 1 over 1 minus 2x, and both of these are geometric series. This would be 1 plus x squared plus x to the 3rd, and so on. And then the second series would be replacing every x with a 2x. So I get 1 plus 2x plus 2 squared x squared, and so on. So multiplying these two series together, I get 1. Then how can I get an x term? I can get an x term by multiplying something in the first parentheses with something in the second. So I could do 1 times 2x, or I could do x times 1. So those are the two different ways to get an x to the first term. When I FOIL everything out, how do I get an x squared? Well, I can get an x squared 3 different ways. I could do 1, here I'll do a star. So I could do 1 times this term. So the starred terms can multiply, give me an x squared. So I get 2 squared times 1 from the stars. Then I could do lightning bolt. Lightning bolt, that's an x to the first power, times this lightning bolt, x to the first power, also gives me an x squared. So I get 2 times 1 from these two lightning bolt terms. And then I could do squiggle times squiggle to give me another 1. You can keep doing this argument. You can go on as long as you want. You can get as many terms as you like. This time I think I get 1 plus 3x plus, what is that, 7x squared, and so on. So you can multiply a series. I'd like to finish with one more example of integration. So this will be the last example I'll do where I could take known series and integrate, differentiate, or multiply to get a new series. Let's approximate the integral from 0 to 1 of e to the negative x squared dx to within 1 over 100 of the true answer. Now, this integral is impossible to do analytically. It's impossible to write a function down that has antiderivative what you want. It's not a possible integral. You have to approximate. Nevertheless, this is a very important integral. This is the bell-shaped curve that you might see in statistics. And in statistics and probability class, you need to do these integrals. It gives you important information. Here's how I would do this. I'd use series. So this is a great example. Check this out. I'm going to replace e to the negative x squared with its Taylor series centered at 0. So we know from the top 3 Taylor series, in fact, this is the number 1 Taylor series, e to the x, that the series for e to the x is x to the n over n factorial. In this case, I have e to the negative x squared, so I'll put negative x squared in for the x. So the first step, I used my known series for e to the x. Let me simplify a little bit. This is the integral from 0 to 1. The sum, n going from 0 to infinity, negative 1 to the n, x to the 2n power over n factorial. Now, integrating series is wonderful. You just integrate term by term. So integrating term by term, I get the sum going from 0 to infinity. I still have a minus 1 to the n. I still have an n factorial on the bottom. The only thing I'm going to do when I integrate is operate on the x. So this becomes x to the 2n plus 1 divided by 2n plus 1. And I evaluate at 0 and 1. So I plug in 1. Plugging in 1 gives me the sum n going from 0 to infinity, negative 1 to the n over n factorial times 1 over 2n plus 1. Then I subtract and plug in 0. But if I subtract and plug in x equals 0, I just get 0. Every term has an x in it, so I get 0 times everything. So this right here, this series, is the exact answer to this problem. I actually don't know any other way to express the exact answer other than a series. So this is the only way to write down the full and complete answer to this problem without an approximation. But I asked you to approximate the answer to within 1/100th of the answer. So let's write down the approximation symbol and just plug in some values. So if I plug in n equals 1, I get, if I plug in n equals 0, I get 1 over 0 factorial, that's equal to 1. And if I plug in n equals 0 here, I get 1. The next term would be minus 1 over 1 factorial times 3. The next term would be plus 1 over 2 factorial times 5. The next term, minus 1 over 3 factorial times 7. And I'm getting kind of bored of writing this down, so I'm going to just stop. I'm going to say, this is my approximation. This right here. Now, this happened to be an alternating series. You may remember alternating series are the easiest kinds of series to approximate. This is within the next term, which would be 1 over 4 factorial times 9. That is a number that's less than 1 over 100. If you actually calculate 4 factorial times 9, it's less than 100. So this is within 1/100th of the actual answer. The only reason that I'm able to do that was because I happen to have an alternating series. And that's very nice. Now, if you're using a computer or if you have more time or if you really want to get super accurate, of course you add more terms in. But I know that if I stop at this term, I'm at least within my acceptable error range. Okay, great.